Hello, so I'm back with another original question. So this question has been designed by my friend who would rather go by the pseudonym of Kiki Kaczynski. Okay, so this question is about hot and dry noodles, which is a popular dish enjoyed in Wuhan, China. So so I think Wuhan has gotten a bad name, right, for the recent coronavirus, right, being first detected there. But actually, the cuisine in Wuhan can be very interesting too, and that is the subject of our question today. So recently, the government has decreed that the pH of such noodles must fall within the range of 7.2 to 9.2. So this noodles is alkaline, right? And scientists decided to test if a sample of these noodles met the criteria set by the government. Okay, the figure above shows a typical bowl of hot dry noodles. Okay, very nice illustration. Suggests the reason why pH indicators such as universal indicator cannot be added to the noodles to determine their pH. We have to understand this, you have to understand how pH indicators work and why pH indicators cannot be used, right? pH indicators such as universal indicator, correct, arise due to a color change. So the thing is, right, that this color change has to be visible, correct? However, as you can see from the photo, now we know why they added the photo, right? The hot and dry noodles are brown in color, right? And very dark and delicious brown color. So it is likely that any color change, right, that the pH indicator will undergo would be very difficult to see and be obscured by the delicious brown sauce, right? And so that is why it cannot be used to determine their pH. So okay, let's read down the question. Sodium hydroxide is a common additive to Chinese noodles to impart a unique texture, right? And I'm sure that some of you may know those kind of alkaline noodles as yellow noodles, right? Commonly used in soup prawn noodles, Hokkien fried prawn noodles, right? And braised noodles and other such delicious and delightful noodle dishes. So okay, let's go back to the question. During the process of making noodles, the noodles are soaked in sodium hydroxide solution. Okay, calculate the range of masses of sodium hydroxide that may be added to 1 liter of water. Okay, so 1 liter is normally a cooking measurement, right? In chemistry, we'll call it 1 dm cube. Right, so it's basically you want to add some sodium hydroxide to 1 liter of water so that the pH falls within the permissible range, right? So the permissible range has a highest boundary of 9.2, a lowest boundary of 7.2 on the pH scale. So this translates to a concentration of H plus, right, to be 10 to the power negative 9.2. Concentration of H plus will be equals to 10 to the power negative 7.2. And remember that as long as it is in an aqueous equilibrium, right? Aqueous equilibrium, concentration of H plus and concentration of OH minus will be equals to Kw, which is equals to 10 to the power minus 14 at 298 Kelvin. So throughout this question, we'll just be assuming 298 Kelvins, right? Why? Because the scientist is most likely doing it at such conditions. So concentration of OH minus, right, would be 10 to the power of negative 14 minus 10 to the power 9.2, right? Then I'll get you 10 to the power negative 4.8 for this one, and 10 to the power of negative 6.8 for the lower boundary. So okay, let me shift a bit more to the right, and then we can easily equate this to the concentration of NaOH. Why? Because NaOH is a monoacidic base, right? That means 1 mole of NaOH only gives off 1 mole of OH minus, exactly, right? Because it's a strong base as well. So the mass of NaOH, right, needed in 1 liter, because this concentration is in mole per dm3, right? So just nice, it shows the amount, right, of NaOH needed per dm3. So you need to convert this to mass, right? So we just multiply it by the MR NaOH, which is 23 plus 16 plus 1, and the upper boundary will give you 6.34 times 10 to the power minus 4 gram, and the lower boundary, right, if you do the calculations, will give you 6.34 times 10 to the power minus 6 grams. So you may be surprised that there's such a big difference, right? It's 2 orders of magnitude, right? Kind of room for error, and that is not surprising when you consider that the pH scale is a logarithmic scale, right? So even small changes on the pH scale, right, can actually signify pretty large changes in concentration. That is why, right, it is not it's not the best way, right, if you have some concentrated acid on the skin, right, to run it under water. Why? Because yes, water will dilute it, however it requires quite a lot of dilution to get the pH to something more favorable to your skin. In fact, a better way to clean up acid spills, right, okay, it's maybe not on your hand, maybe on the floor, right, would be actually to neutralize it with an insoluble base. Okay, but anyways, I digress. Let's go back to this question. A sample of the water used to soak the noodles was titrated against tartaric acid solution. Okay, tartaric acid is an organic acid, and it's another common food additive, right? And you can actually find like tartaric acid containing baking essentials, right, in your nearby baking shop. So tartaric acid consists only CH and O atoms, right? These two information is actually supposed to be provided by the question. It's just that my friend forgot to include it in, so I included it after consulting with him and telling him that this information is necessary. So synthetic tartaric acid exists as a mixture of 3 stereoisomers, though only one stereoisomer is found in nature. So remember, stereoisomer, there's 2 types, there's cis trans and there's enantiomers. But normally, right, the number of stereoisomers equals to 2 to the power n, where n plus m, where n is the number of chiral centers and m is the number of double bonds, right? So this would suggest that normally it is a even number of stereoisomers. So what do you mean? What does it mean when there's an odd number, right? 3 stereoisomers, it means that it is usually a plane of symmetry, right? So one of the stereoisomers, right? So you have, say, A, and then A's mirror image B. But you also have C, which is a meso compound with a plane of symmetry, right? So A and B don't have a plane of symmetry, and they are stereoisomers of each other, enantiomers. But C is a meso compound, right? A meso compound which has a plane of symmetry, and it does not have a non-superimposable mirror image. So it does not have, like, say, a counterpart enantiomer. So 3 stereoisomers. So I propose that there's 2 chiral centers, and the meso compound has a plane of symmetry. So let us look more at it, because this information is just not sufficient, right? So tartaric acid shows no reaction in Tollens reagent, so no aldehyde, or 2,4-DNPH, so no ketone. Then 1 mole of tartaric acid is combusting in excess oxygen gas. The resultant volume of gas increased by 36 dN³ after the gases were cooled to room temperature. And this is very important, right? Why? Because any water produced will now be liquid and not in gaseous state. 54 grams of water was also collected. Okay, so very conveniently, Zhi Jie gave us 1 mole of tartaric acid to work with. So 1 mole of tartaric acid, let it be CXHYOZ, right? Plus a certain amount of O2 to form XCO2 plus Y/2 H2O. So how many moles of CO2 will react with 1 mole of tartaric acid? It is simply 2x plus Y/2 minus Z divided by 2, right? You agree with me? Why? Because it needs to provide 2x for the CO2, it needs to provide Y/2 oxygen atoms for the H2O, but yet you can use some of the oxygen atoms in tartaric acid, correct? But you divide by 2. Why? Because 1 oxygen molecule has 2 atoms of oxygen. So we can begin, but this one, it is liquid, remember, when it's cooled down to room temperature. So which are the gases? This is a gas, this is a gas. Tartaric acid, while most organic acids are solid in state, correct? Or even or at most a liquid state, hardly gaseous. So we can then say that the change in the volume of gas, right, by Avogadro's law, is proportional to the change in the total number of gas molecules, of total amount of gas, right, in moles, and that is equals to the final minus the initial, right? So what is the final amount? The final amount is x minus the initial, so minus 2x plus y over 2 minus z over 2. And what do you get? You get z over 2 minus y over 4. Okay, so y over 4 moles. And we say that this change is 36 dm cube. Okay, so 36 dm cube, but now we need to convert 36 dm cube. So this corresponds to 36 dm cube, but we need to convert 36 dm cube to number of moles, right? So we can equate. So we can use the equation of state PV equals to nRT, assuming that they're ideal gases, right? Most of the time, calculations on gases is always assuming they're ideal gases. If not, it will be quite troublesome to calculate, right? You'll need new relationships like the Van 't Hoff equation, which is not in the syllabus, so they have to give you if they ask you to use it. But I digress once again. So N equals to PV over RT equals to, what is the pressure? I assume it's atmospheric pressure 101325, the volume 36, but convert to meter cube, because remember PV equals to nRT takes in values in meter cube divided by R, right? And the temperature, room temperature, right? This is cooled to room temperature. So what is this value? We get 1.473025 SF. So this is our first equation. However, we need like some more equations, right? We can't solve directly. So is there more information that they give us? Right, very thankfully, Kiki Kaczynski gave us one other piece of information, which is 54 grams of water was also collected. So normally, if the setter provides us another piece of information, it must be used, and indeed, we do need another piece of information, so let's use it. So this means that y over 2 moles of H2O, right, corresponds to 54 grams, okay? So 54 grams equals to how many moles, right? In number of moles is 54 divided by 18, right? The mR of water, right? Which will give 3 moles. So what does this mean? This means that y over 2 equals to 3. And therefore y equals to 6. And substituting this into here, z over 2, right, minus 3 over 2 equals 1.4730. So if you do the maths, right, bring this over to the other side, so it's about 3 times 2 is about 6, so z equals to 6, correct? If you type, actually it's 5.99, which is very close to 6, approximately 6. So now we have Cx, right, H6O 6, right? So we don't know what x is. Okay, so let me try. Let's say x equals to 3, right? So let us assign 2 acid groups, right? Because we need to get rid of the 6 oxygens, and we know if x equals to 3, how many degrees of unsaturation are there, right? There's 1 degree of unsaturation. But then we realize that we already have 2 degrees of unsaturation, right? So let us maybe instead have a lot of oxygen groups then. 1, 2, 3, 4, 5, 6. Okay, so does this work? Okay, how many chiral centers are there? There is none. Okay, so this actually poses us with a bit of a problem, right? Alternative, because we know that there are stereoisomers, alternatively, perhaps we can shift one oxygen group right over here, correct? Wow, this is okay. To organic chemists, right, this is a disaster, right? Because it's so unstable. So, but is this a possibility, right? Even though I'm highly skeptical, right? Wow, 3 OH groups bonded to 1 carbon seems very, very suspicious. But yes, there's a chiral center, but is there 2 chiral center with a plane of symmetry? No, that is not. So x equals to 3 is most likely not the case. Let us try x equals to 4. So in this case, right, x equals to 4 corresponds to 2 degree of saturation, right? So we can give two carboxylic acid groups, right, for the 2 degrees of unsaturation. 2, 3, 4, that's 4 oxygen atoms, 2 more lead, because remember there is no carbonyl group, so we just assign them as alcohols. Okay, so does this fulfill the criteria? Is this a chiral center? Yes, this is also a chiral center, and there's a meso compound, correct? There's a meso compound where there's a plane of symmetry. Correct, there's a plane of symmetry, right, in the meso compound, and so there is, how to put this, 3 stereoisomers, correct? Because originally there's 2 chiral centers, so number of stereoisomers would we expect 2 to the power 2, but because there's 1 stereoisomer which has a plane of symmetry, you need to minus 1 because it does not have its corresponding non-superimposable mirror image. It gives us 3. So okay, we got our structure for a tartaric acid, right? Actually, tartaric acid is not really related to cream of tartar. I realized, right, the delicious cream of tartar sauce which people eat with fish and chips, right? I realized that actually, much to my disappointment, that it has nothing to do with tartaric acid. In fact, the sourness, right, of that does not come from tartaric acid, but most likely citric acid, right, from a lemon. Okay, so much to my disappointment. Okay, but let us continue. I digress once again. Okay, deduce the structure of tartaric acid that has been done. State its molecular mass, right? So it's C4H6O6, right? So C4 MR of C4H6O6, right? 4 times 12 plus 6 plus 6 times 16 will give you 150. You can either leave it as CSL or put it as 1dp, right? Because why 1dp is a convention for MR. I think either of them should be fine. And then okay, its molecular mass 150, right? So note that don't give the units of gram per mole, right? Because this is relative molecular mass, right? So relative molecular mass is actually a ratio, so it's unitless. But the absolute value of the relative molecular mass is equal to the molar mass, right? Molar mass having units of grams per mole. So just a bit of a throwback to secondary school stoichiometry in units. So let us take a look at the next part. 25 cm³ of the water used to soak the noodles required 16 cm³ of this concentration, right? Note the concentration is not in mole per dm cube. How irritating, right? Kiki Kaczynski made our life a bit more difficult. Solution of tartaric acid for complete reaction. Okay, calculate the concentration of hydroxide ions in the solution, hence determine if the noodles meet the pH requirement. So we know that hydroxide ions react with the tartaric acid, which I would draw the structure once again. Right, so does the sodium hydroxide react with the OH groups over here on the 2 alcohol groups, right? No, they do not, right? They only react with the carboxylic acid group. So tartaric acid is a dibasic acid. Let us express it as H2A, okay? To show that there's 2 sort of protons which react with NaOH. So that the concentration of tartaric acid in mole per dm cube be the concentration in gram per dm cube, right? Divided by the molar mass, which is equal to molecular mass of 150 gram per mole. So if you are a bit confused as to whether to divide or times or whatever, just check your units, right? Gram cancel out. 1 over per mole gives you mole and gives you mole per dm cube. So wonderful, and that is lovely because we can get a value out of 0.0016667 mole per dm cube. So the concentration of, or rather the amount of H2A that has reacted, right, is simply a 16, right? This is a classic kind of thing that you always do in titration, right? From now on, it's just really a standard titration question, right? The volume in dm cube times the concentration gives you wow, so many zeros. Maybe I really should write in a scientific notation, but I'm a bit lazy. Okay, so in moles. So however, the amount of NaOH that's reacted, remember, 2 moles of NaOH react with 1 mole of tartaric acid, so you need to times 2. So 0.0000533 moles. Okay, so wonderful. What is the concentration of hydroxide ion? It's simply the number of moles divided by the volume. What is the volume? 25 cm3, right? Convert it to dm3 by dividing by 1000. It gives you 0.0021333 mole per dm3, and because NaOH, right, is a strong base, so strong alkaline, so this is equal to concentration OH minus, so POH, why did I put an additional dot there? Confusing. POH equals to negative log of that value over there, 0.0021333 equals to 2.67. At 298 kelvins, right? pH plus POH equals to 14, right? So pH equals to 14 minus 2.67 equals to 11.3, and we realize that it's out of the pH requirement. What is the pH requirement? It's 7.2 to 9.2, right? Oh my, 11.3 is way out of the range. Right, so eating these noodles will probably be a pretty uncomfortable experience. I don't think it's very tasty. Right, imagine it's at about, yeah, it is, wow, it is as alkaline as this concentration of sodium hydroxide, right? 0.002 mole per dm3. It is pretty alkaline already, right? So I don't think it will taste good. Okay, so I have finished my work solution to this question. I hope you enjoyed this video and that it has been helpful to you. Alright, thank you. Alright, I'll go to sleep now.